Hey everyone, welcome back to the next part of chapter 10 here in your calculus book. And today we're going to be looking at the power series that we looked at on our last lesson. And we're going to do some more calculus with them. Some honest to God calculus this time. So we'll see you in the next screen. Okay, so we have a couple of fractals here, and Archimedes' theorem states that the total area under a parabola is 4/3 the area of the blue triangle. He then determined that each green triangle, you can see over here, has 1/8 the area of the blue triangle. Each yellow triangle is 1/8 the area of the green triangle, and so forth and so forth. So we keep on multiplying the area by 1/8 in order to get the next smaller shape. So assuming that the blue triangle has an area of 1, the total area here would be an infinite series. So here's one place where we can use an infinite series. And the Koch snowflake, at least the first 4 iterations are shown over here. And each iteration is going to add a set of triangles to the outside of the shape. The area inside the Koch snowflake can be described as a union of an infinite number of equilateral triangles. And in the diagram above, triangles are added in the second iteration are exactly 1/3 the size of the largest triangle, and therefore have exactly 1/9 of the area. And similarly, each triangle added to the second iteration has 1/9, so multiplying by 1/3 again, and so forth and so forth and so forth. So keep on adding 1/3. Taking the first triangle as a unit of area, what's the total area of the snowflake? Again, since we're adding things and the things that we're adding is a multiple of the previous thing, this is an infinite series. So that's just kind of an into. The problem really begins with this part right here where it says, let's start with our basic geometric series, which is 1/1 minus x. And it says to write out the first 4 terms and the general term. We did that a lot last time. So we got 1 plus x squared plus x cubed plus x to the n. Now here's where the calculus comes in. If we want a series for the derivative of f, then we could take each derivative or the derivative of each term, and that creates a whole new series. So from old series, we can get new series. So the derivative of 1/1 minus x equals the derivative of each individual term. Now all we need to do is take a derivative of each one of these expressions. And there we go. We have just created a series for -1/1 minus x squared. Now we kind of notice that this first term is going to be 0. So non-zero terms are usually not included, or 0 terms are not usually included in our series. So we'll have to have a discussion about what happens here, because in essence, this is really the series right here. Okay, so can we write out the first 4 terms and the general term for the series of -1/1 plus x quantity squared? Well, I believe we just did. Oh, no, we didn't. Hello. Kind of read this carefully. This is 1/1 plus x. And the previous one we did was 1/1 minus x. So we'll need a series for 1/1 plus x. Thankfully, we did that series last time we met. And we're going to go a little bit slowly here so we can get the full effect of what's happening with the derivative. I want you to notice that I also included the 5th term of the series, because I know that the first term, 1, the derivative of that's going to be 0. And I need 4 terms. The derivative of the left is equal to the derivative of the right. So I've taken the derivative of the first 5 terms. We already said that the derivative of 1 is 0, so I didn't bother writing it here. But now let's take a look at the general term, and let's figure out a derivative. -1 to the n doesn't have any x's involved in it. So that's actually constant in terms of x. So I'm just going to write it out. The only thing that I need to take a derivative of are the factors that have an x. And this second factor, x to the n power, certainly has an x. So the derivative of anything of x to any power is the power multiplied by x to the decreased power, n minus 1, and then multiplied by the derivative of x, which is just equal to 1, so we don't have to write the chain rule. So here is our series, a new series formed by taking the derivative of an old series. Now don't worry about memorizing this particular one. This is a derived series is what we would probably say. So, memorizing this one is not going to be important. I will definitely let you know when we see a series that you should memorize. Clearly, 1 over 1 minus x and 1 over 1 plus x are two of those series. Coming around on the other side of calculus, we know that natural log of 1 plus x is going to be the antiderivative of 1 over 1 plus x. So can we use that information to find a series for natural log of 1 plus x? Well, firstly, what is the series for 1 over 1 plus x? We just did that. Be a little careful here because we have plus signs in between each term, so we got to make that negative x and negative x cubed. Okay, next. We're going to replace x with a dummy variable t, and then we're going to integrate from our polynomial from 0, which happens to be the center of the series, to x. So the antiderivative from 0 to x of 1 over 1 plus t dt is the integral from 0 to x of 1 plus negative t plus t squared plus negative t cubed plus ... all the way to negative 1 to the n t to the n power. Now we're just going to take a term-by-term integration. The derivative of the left side is the natural log of 1 plus t from 0 to x. This is kind of presuming that x is greater than negative 1. Now the first four terms on the right side are t minus 1/2 t squared plus 1/3 t cubed, etc. That's not that difficult, but how do we take the antiderivative of negative 1 to the n multiplied by t to the n? Just like derivatives, negative 1 to the n doesn't have a t involved, so I'm going to treat that like a constant, so I'm just going to write it, negative 1 to the n. Now the antiderivative of anything to the n power is 1 over the increased power by 1 multiplied by t to the new power n plus 1. And we're going to integrate from 0 to x. Okay, so the left side from 0 to x is equal to the right side from 0 to x. We're going to substitute. So we're substituting x and 1, or x and 0. Now taking a look over here on the left side, the natural log of 1 plus 0 is the natural log of 1, which itself is 0. So the left side, that's just going to be natural log of 1 plus x. Now on the right side, if we take a look at the second bracket, every term gets multiplied by 0, so this is going to be 0 as well. And the fact that that second bracket turned into 0, that happened because we chose 0 as our lower limit of integration. That's always going to happen if you make the lower limit 0. Sorry, if you make the lower limit the center of the series. And that kind of does it. Now we have a series for the natural log of 1 plus x. And it really wasn't all that difficult. We just had to be a tiny bit careful with our integration. This would have worked no matter what you chose as your lower limit. However, it would have been a little bit it would have been more difficult to get to this result. So choosing the lower limit as the center of the series makes the process go a lot easier. So what is this series for natural log of 1 plus x? Well, as you see, the natural log of 1 plus x is equal to x minus 1/2 x squared plus 1/3 x cubed, etc., etc. This is a good time to mention that series aren't unique. In other words, more than one series could be equal to the natural log of 1 plus x. This is just one that we found, but others may or may not exist. And then here's your pro tip again. When integrating to find a new series, always set the lower limit to be the center of the interval of convergence, because things will cancel out better that way. So important for us also, if you remember that the series 1 plus x plus x squared, etc. If you remember that only converged for x between -1 and 1, then any series that you create using differentiation and integration is going to have that same interval of convergence. So you don't have to redo an interval of convergence if you knew the interval of convergence of the series that you began with. Sorry, I just noticed a typo here. That should have been 1/1 minus x. So we got that. Okay, exploration time. Let's write down a power series that represents 1/1 plus x. The hint is this is a geometric series. So I'm just going to make the function equal to the geometric sum. So a/1 minus r equals 1/1 plus x squared. And then I need to figure out what values of a and r will make this true. And it looks as though this is going to be true if a is equal to 1 and if r equals -x squared. So 1/1 plus x squared, that's equal to 1 minus x squared plus x to the 4th minus x to the 6th plus the quantity of -x squared to the n, which I don't like because inside that power we've got negative and a second power. So I'm going to simplify that first by simplifying the negative part. So that's -1 to the n, x squared to the n. And then I'm going to use properties here of exponents. So x squared to the n, that's the same thing as x to the 2n power. So here is my power series to represent 1/1 plus x squared. Next, we're going to replace all the x's with the dummy variable t, and then we're going to integrate the first 4 term and the general term from 0 to x. You probably didn't need to know that we're integrating from 0 to x, because if you look at the series, the center of the series is clearly 0, so that's definitely going to be your lower limit. So let's just integrate. Let's set up the integral to start off with. So we have our antiderivative. The only weird one here is t to the 2n, and the new power here is going to be t to the 2n plus 1. So we also divide by t to the 2n plus 1. And notice that if I substitute 0, each of these terms has a t. So each of the terms when I substitute 0 is 0. So I'm going to just keep that and only write down when I substitute x. And there we have it, a series for the antiderivative of 1/1 plus x squared. And to put it all together, if the antiderivative of 1/1 plus x squared is arctangent, then what is the series for arctangent? Well, there we go. It's just our result from our previous part of the problem. Some textbooks are going to tell you that this is a series you have to memorize, and I kind of disagree. This series isn't one of those series that is going to make a big difference. If you have nothing else to do with your time and you just feel like memorizing series, then by all means you can memorize a series for arctangent. but it's really not that important, I don't think. There are definitely other series that are more impactful than the series for arctangent. Okay, over to the exploration. Let's start by evaluating f of 0. And that's not really difficult. The only term that doesn't have a x in it is that first term. So f of 0 is equal to 1. Now we're going to find the derivative of f of x. So f prime of x is a derivative of 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc. And this just takes a term-by-term differentiation. So I've taken the derivative of each term, and I've written out the factorials kind of as far out as I would go here. There is a ellipsis over there. So now we can simplify things. We can cancel out the 0, of course, and then in the second term, 2x over 2 times 1, well, that's just equal to x. And then in the fourth term over here, we've got the 3, and that can cancel out with the 3 from the factorial. So that's x squared over 2 factorial. And we keep on going with that next term, which I kind of added in there. But the 4 will cancel out from the 4 factorial. And I see I made a mistake with the power, but that simplifies to x cubed over 3 factorial plus, and I'm just going to say ... here. The pattern's pretty clear, but what the heck happened here? F prime of x equals 1 plus x squared over x cubed over 3 factorial, etc. But isn't that the same thing as f of x? So is there a function that behaves like this where f prime of x is equal to f of x? And I'll give you a hint. The derivative of e to the x is equal to e to the x. So, is there a function that behaves that way? Yes. Did I just back into the series for a well-known function? Also, yes. The function, or the series for the function e to the x, that's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way to x to the n power over n factorial. And while we're at it here, we should probably simplify this term right over here. So if I have n over n factorial, I can expand that to n over n times n minus 1 times n minus 2 times n minus 3, etc., etc. Like in the previous, or what we just saw, those n's can cancel out. And that's the same thing as 1 over n minus 1, n minus 2, n minus 3, etc. And that gives me the simplification n over n factorial is 1 over n minus 1 factorial. You're going to need to do those kinds of simplifications eventually. This brings us to our important ideas. So differentiation and integration of a power series basically allows you to form new series. And those new series will have the same interval of convergence as their parent series. When you differentiate, if the first term happens to be constant, it's going to be lost. And if that happens, you want to notate that the series index have changed from 0, 1, 2, 3, etc. to 1, 2, 3, 4, etc. So the first index numbered term gets eliminated from the list. Now integration, the tip that you need to use there is that the center of the series has to be the lower limit. And then if you do have x minus a, if your center is not 0, then you're going to want to make a u substitution, and you're going to allow u to equal x minus a. Finally, we have the second series which you need to memorize. So you have e to the x is equal to 1 plus x plus 1 over 2 factorial x squared, etc., etc. You have to memorize this one. No one who ever got a 5 on an AP test didn't have this memorized. Maybe I should have said everybody who gets a 5 is going to have this e to the x series memorized. So you really need to have that memorized. Check your understanding. We have a 3-part question. So number 1 is to write a function, and the helper here is a geometric sum represented by the series, and then you want to make sure that you write the first 4 terms and the general term. That's in quotes because pretty much every AP problem is going to have that exact same standard. First 4 terms and the general term. So you need to get used to writing the first 4 terms and the general term for every series that we look at from now on. So for part A, I noticed that the series is not written out. It's given to me in sigma notation. So a good idea is to write out those terms. Okay, so let's write out those terms. We've got when n equals 0, we got 3x to the 0. When n is 1, we have 3x to the first power. When n is 2, we have 3x to the second power. We get a 3x to the third power, and then our general term. Reminder that the general term is the same thing as what you see in sigma notation, so you don't really have to think about it. The next thing that I'm going to ask you to do is to simplify this so that the only thing in the parenthesis, or the only thing receiving the power, is going to be x. Okay, so 1 plus 3x plus 3 squared x squared, 3 cubed x cubed, all the way to 3 to the n, x to the n. Like we discussed on the previous lesson, there's no reason for you to, simplify those exponents. Just leave it the way it is. So do we have the first 4? No, do we have the function? No, we don't have the function, but we know the first term is 1, and we know that the common ratio is 3x. So we can write that series, the geometric sum, really easily. That's just 1 over 1 minus 3x. So I think that's part A, and we're good. Part B says to differentiate the series and find the series for the derivative. So this time I'm going to actually multiply out all the powers. I mean, the powers of 3, I've got that pretty well at hand. And then I'm also going to add the 5th term here, 81x to the 4th power, because I know when I take the derivative, this first term is going to be 0. So a little bit of pre-work here. And then also on the left side, I've gone ahead and I've made this into a form where it's easier to take the derivative, because I'd rather use the power rule than the quotient rule. So let's take our derivatives. On the left side, we get negative 1, 1 minus 3x to the negative 2, multiplied by the derivative of 1 minus 3x, which is negative 3. On the right side, we get the derivative of 1 is 0, the derivative of 3x is 3, the derivative of 9x squared is 18x, and I made a mistake here, that should just be 18x. And then the derivative of 27x cubed is just 81x squared, and then the derivative of 81x to the 4th is 324x cubed. And I've left the general term so we can do that together. We've got 3 to the n power, which doesn't have an x, so it's constant, multiplied by, and we're going to use the power rule here for x to the n. That's n, x to the n minus 1 plus etc., etc. And that kind of completes the problem. We've got the series for 3 over 1 minus 3x quantity squared is, of course, 3 plus 18x plus 81x squared plus 324x cubed, etc., etc. Part C says to integrate the function and the series to find the series for the antiderivative. The integral from 0 to x of dt over 1 minus 3t is the integral from 0 to x of 1 plus 3t plus 9t squared plus 81t cubed plus, and then all the way down to 3 to the n, t to the n. Now the right side here is actually going to be easier to integrate than the left side. On the left side, we're going to say u is equal to 1 minus 3t. So du is equal to negative 3 dt, or dt, we can replace that with a negative 1/3 du. Also, we can say when at the lower limit, u of 0 is going to be 1, and then u of x, that's going to be 1 minus 3x. Which seems like it's going to be a problem. It's not. So my left side becomes the integral from 1 to 3, 1 minus 3x of 1 over u du. Actually, I forgot the 1/3, the negative 1/3. Let's put that right there. And then the right side I've already integrated. Integral of 1 is t, 3t is 3/2 t squared. The very last, the general term, 3 to the n is constant, and the antiderivative of t to the n is 1 over n plus 1 multiplied by t to the n plus 1. So that left side is the right side finished. Let's integrate the left side. On the left side, I get negative 1/3 of the natural log u, and that's going to go from x equals 1 to x equals 1 minus 3x. And on the right side, I'm going to substitute x, and notice that each term here has a t in it. So when I substitute 0, I'm going to get a 0 in return. So I'm not going to bother with the second part of this substitution. All I need to do now is substitute on the left side. So negative 1/3 natural log of 1 minus 3x plus 1/3 the natural log of 1. Of course, the natural log of 1 is 0. And if I multiply both sides by 3, negative 3, I now have a series for natural log of 1 minus 3x. Notice that I didn't bother distributing the negative 3 onto the right side. Not really important since that's a constant. So that's it for us today. We've definitely had a really good look at differentiating and integrating power series. So yeah, I hope everything works out for you, and I'll see you next time.